All right, good afternoon, everyone. I hope you all enjoyed your lunch. My name is Hyung No, and I am a first-year PhD student at Seoul National University. So today, I'll be introducing my paper, PID-Comm, a fast and flexible collective communication framework for commodity processing and DIM devices. I presented this paper at this year's ISCA just last month, and I am thrilled to have the opportunity to share it again here. So today, many systems suffer from what is called the memory wall. The memory wall refers to the phenomenon where processor performance is increasing rapidly, but memory performance isn't quite following. As many AI applications require high memory bandwidth, the memory wall is becoming more and more the dominant bottleneck. So one solution to the memory bottleneck is processing in memory. Now, I'm sure that we're all familiar with what processing in memory is. So the bottleneck figure is what we configure the processing in memory hardware should look like. So when computing on PIM-based hardware, as PIM consists of multiple cores, the workload should be distributed to each DPU for computation. And in many cases, after each layer of computation, we need to share the intermediate results for further processing. Then how do we share the results between the DPUs? Well, one most common solution to this would be collective communications. Collective communications, such as all-reduce or all-to-all, are crucial for efficiency and performance when it comes to sharing data across nodes. However, collective communications or inter-DPU communications in general show low performance on modern processing and memory architectures, as there is no direct path connecting each of the processing units. Due to this, the host processor works as a medium for inter-DPU communication, making it the bottleneck of major applications. To relieve the bottleneck, we need a faster method of inter-DPU communication to reduce the overhead, and this is where PID-Comm jumps in. So, PID-Comm targets frequently used collective primitives and proposes several techniques to accelerate them for faster communication. A sneak peek of the evaluation shows that PID-Comm achieves a geomean speedup of 2.83 times compared to the baseline implementations. Throughout the presentation, I will show you how this was possible. Now, just a quick view of the contents, and now I will cover some of the background of the talk, followed by the motivation of the study. So, PIM-enabled DIMMs, or UPMEM DIMMs, refer to PIM cores implemented on dual inline memory models. Other than the additional processing units, they share the same hierarchy as DDR4 DRAMs. In a single rank of each DIMM, an 8-bit bus per chip is concatenated to form a 64-bit channel bus. Due to its inner structure, the same bank of each chip in a rank are accessed at once. So we name the group of banks accessed together as entangled groups. So if you were to send a 64-byte cache line of data to the banks, each 8-byte word will be split to each bank in the entangled group. Notice how the words in the banks are not interpretable. In the other way around, if the words are complete in the banks, they will be split in the host memory. To fix this, a reordering of data in a transpose-like way is essential, and we refer to this as domain transfers. Now, the issue with domain transfers are that they are extremely slow, as they tend to put an extra burden to the host CPU. Now, UPMEM did a terrific job of accelerating them by implementing them using AVX SIMD instructions, but they are still causing a lot of overhead. This becomes a problem as inter-DPU communication requires domain transfers to modulate data. To check how conventional inter-DPU communication works, we show an example of an all-to-all operation implemented using the UPMEM SDK library. So first, the data in the banks are moved to the vector registers where it is domain transferred. Then the data is stored in the host memory where it is modulated. And finally, the data can travel back the way it came from the host memory to the vector registers, domain transferred, and then stored back in the banks. Notice how 2 domain transfers were required in the process, leading to low performance. To exemplify the effect of naive inter-PE communication, we perform a breakdown on 5 benchmark applications. Our measurements show that communication accounts for an average of 76% of total execution time. Further breakdown shows that over 80% of the communication overhead stems from host memory access, data modulation, and domain transfer. Additionally, we found that some applications require a more flexible communication model to enable communication along different axes of nodes. We show an example of such an application, a simple GNN inference application below. So first, we choose to divide the feature matrix into left and right halves and distribute it to the nodes as depicted. Naturally, each node will receive a portion of the graph, and computation is done as the following. To repeat the computation structure of the first half of the layer, we choose to all gather the nodes through the vertical axis, like this. Naturally, the remaining computation will be done as depicted. Now, the resulting feature matrix is to be fed into the next feature matrix of the next layer. So, in order to match the shape of the feature matrix, this time we choose to all gather the nodes along the horizontal axis. Now the feature matrix may be fed into the next layer. This example shows that a flexible communication model is essential to support diverse applications that require communication across multiple axes and invoke multiple communications at once. So overall, we saw that conventional inter-DPU communication is slow and it needs to be flexible for practical use. So what we aim to do is to optimize these communication patterns to make them fast and wrap them into a nice communication model to support flexible use. So now we will move on to our main idea of the talk. But before introducing our main scheme, I would like to briefly cover the baseline implementation of inter-DPU communication, which can be implemented using the UPMEM SDK library. The figure below shows how Alt-Flow is performed across 4 DPUs using a conventional communication method. And it's very similar to the conventional method that we saw just before, but this time it is much more detailed. So first, the data located at the same index of each DPU are sent to the vector registers, and the host CPU will perform domain transfer on it. Then the data will be stored in the host memory, where the host will freely reorder the data. This way, we can obtain the final form of data in a contiguous memory space. However, data modulation involves a lot of global rearrangements or accesses to multiple cache lanes at once, which degrades performance. Afterwards, the data is sent back to the vector registers, followed by a domain transfer, and then the data is sent back to the DPUs, and we have completed our Alt-Flow operation. We can see that the left data layout has changed to the right data layout, matching the Alt-Flow pattern above. So, to accelerate the communications across the DPUs, we propose 3 techniques, 3 optimization techniques. So the first is PIM-assisted reordering, which aims to offload a portion of the data modulation process to the DPUs to utilize its massive internal bandwidth. And just a heads up, the bars on the upper side of the slide show the improvements earned from each step, so it should give you a brief idea of how much impact each technique has. Now, back to our first technique. So first, each DPU reorders its data layout in parallel like this. And now the data is sent to the host vector registers. From here on, the rest of the procedure is similar to the conventional workflow above. We perform domain transfers, save the data in the host memory, and then perform data modulation. Now, one thing to point out here is that thanks to the reordering process done beforehand in the DPUs, the modulation process is now composed of local rearrangements compared to the global rearrangements in the conventional workflow above. This improves the cache line access patterns, reducing overall execution time. Afterwards, the data is sent back to the vector registers, followed by a domain transfer. Then the data is stored back in the DPUs. To complete the Alt-Flow procedure, a final reordering of data reordering in the DPUs are required. Our second technique is in-register modulation. So this time, we aim to eliminate unnecessary host memory access. The overall procedure is the same as before until domain transfer has been performed on the vector registers. Remember how the data modulation process on the top was specific to the cache line. So one interesting fact is that the size of the cache line is the same as the size of the vector register. Hence, if we choose to modulate the data directly on the vector register, we can avoid unnecessary host memory access, bringing improvements in performance. And the rest of the procedure is done the same as above. Our third technique is cross-domain modulation. And this time, we aim to remove unnecessary domain transfers. So the overall procedure is the same as before until the data is sent from the DPUs to the vector registers. On the technique above, we performed domain transfers before and after modulation so that the host can read and interpret the data while it is processing them. But what if the data modulation process is composed of only data reordering? In that case, the host doesn't really have to interpret the data. It can just reorder them in an appropriate manner to get the same results. So in this case, we combine the 3 stages into a single bitwise rotate operation as shown in the figure, removing redundant domain transfers. And finally, we can perform the rest of the procedure to complete the auto operation. Overall, PID-Comm's 3 optimization techniques successfully reduced their target bottlenecks, bringing extreme speed up. But speed up is not enough for us to use the collective primitives in practical situations. So what we need more is a new communication model that supports diverse communication groups and multi-instance invocations. To do this, we propose to organize the DPUs into a hypercube model. So in the hypercube model, the DPUs parallel to any axis or any plane or any shape of a higher dimension can form a communication group, and all the communication groups will communicate within itself all at once. Now, organizing the DPUs to enable this is all about mapping the DPUs to the virtual hypercube. Remember how the DPUs in an entangled group are accessed together for every read or write operation. So in the perspective of inter-DPU communication, if one of these DPUs are involved in communication, we will be reading and writing data from all the other DPUs in the entangled group. So for efficiency, we decide that we should use entangled groups as the basic building blocks of our hypercube. So what we are going to do with the entangled groups is we are going to stack them starting from the x-axis and then work our way up in the order of x, y, and z-axis until the hypercube is completely filled. We chose this kind of mapping as it allows us to implement the hypercube in an efficient manner. So, for example, when we're using the hypercube, the users may first define their hypercube configuration, which in this case is a 4x4x2 3D-dimensional hypercube. After setting the configurations, PID-Comm automatically maps the physical DPUs into the hypercube using entangled groups as the basic building blocks. Now the users can choose how to group the DPUs into a communication group. Of course, this grouping is not permanent and can be changed for every communication invocation depending on the user's needs. So the users may, let's say, communicate along the x-axis for the first invocation, and then in the next invocation, communicate in communication groups parallel to the xy plane. Although the communication groups change, our library can appropriately handle these situations without help from the user. Also, using our library, we can compress complex implementations into just a single line of code while improving its performance at the same time. It is just simple as that. So for more information on the implementation, please refer to our paper or our GitHub repo, which is to be shown on the last page. Finally, I am going to cover the evaluation and conclude my talk. So our evaluations were done on a system equipped with 4 channels of UPMEM DIMMs, and we have used simple PIM and UPMEM SDK-based implementations as our baseline. We also implemented 5 benchmark applications to evaluate our newly implemented primitives on real-world applications. So first, the performance of the primitives. Our newly implemented collective primitives show a geomean speedup of 2.83 times and a maximum speedup of 5.19 times compared to the PIM baseline. We conducted an ablation study and breakdown for further analysis. So each of our techniques, PIM-assisted reordering, reduces the data modulation time, and in-register modulation eliminates host memory access, and lastly, cross-domain modulation removes domain transfers when it is not essential. Each of the techniques showed a speedup of 1.48 times, 2.03 times, and 1.42 times speedup in average. We also applied our primitives to benchmark applications, and applying PID-Comm resulted in a geomean speedup of 1.99 times and a maximum speedup of 3.99 times. Additional breakdowns show that PID-Comm successfully reduces the targeted collective primitives overhead. So, in conclusion, we claim that PID-Comm is the first fully fledged collective communication library for PIM-enabled DIMMs. We provide a micro-level optimizations to accelerate inter-DPU communications and a hypercube communication model for flexible use. Our primitives outperform the PIM baseline by 2.83 times in geomean, and it is currently open sourced on our GitHub page, so anyone interested are welcome to come and have a look. Thank you so much for your attention, and I will be happy to answer any of your questions.